Hey, science fans! Get ready to unlock some of the universe's most fundamental secrets. Ever wonder what powers your phone, keeps your laptop running, creates lightning, those dramatic displays of nature's raw power, and perhaps most surprisingly, holds atoms together, forming the very building blocks of everything we see? It all starts with a tiny, almost unbelievably small property called electric charge. This is the fundamental force at play. Imagine Lego bricks, those simple, colorful blocks we all know and love. Let's say red bricks represent positive charge, and blue bricks represent negative charge. Just like magnets, red repels red, they push each other away, blue repels blue, creating a similar force of separation. But red and blue snap together with a satisfying click, drawn to each other. Opposites attract. This is a fundamental rule of the universe. Protons, found in the nucleus of an atom, are our red positive bricks. They carry a positive charge. Electrons, orbiting the nucleus, are blue, negative ones, zipping around with a negative charge. This push and pull, this attraction and repulsion, is the very foundation of electricity and electromagnetism. Most things around us are neutral, meaning they have roughly equal numbers of reds and blues, so their forces effectively cancel out, leading to a stable state. But what happens when you rub a balloon on your hair? Well, you're actually scraping off some blue bricks, electrons, and transferring them onto the surface of the balloon. Now your hair is left with a surplus of positive charges, making it positive, while the balloon has gained extra negative charges, becoming negative. Voila! Static electricity. Your hair stands up, reaching for the sky, because each strand, now positively charged, repels the others, pushing them apart. And the balloon, now negatively charged, sticks to a wall, seemingly defying gravity. It does this by shifting charges in the wall ever so slightly, a phenomenon called polarization, attracting it and holding it in place. This is all about imbalances, about creating a separation of charge. Separating charges lets us see electricity in action, making these forces visible and tangible. It's not magic or some mysterious force, it's simply science at its most fundamental. All thanks to those fundamental red and blue bricks, the positive and negative charges. Every object you see, every atom that makes up that object, is ultimately built from these simple yet powerful rules of attraction and repulsion. The universe's grand dance of attraction and repulsion, the forces that shape galaxies and hold stars together, all starts here, with these tiny charges. Next time you see a spark jump between your finger and a doorknob, or feel a shock when you touch something metallic, remember? It's not some mysterious phenomenon. It's just those Lego-like charges, those fundamental building blocks of the universe at work. This seemingly simple interaction is the groundwork for everything in electricity, from powering our homes to enabling the technology that connects us all. So let's dive deeper into the fascinating world of electric charge and explore the incredible forces that shape our world and the universe beyond. Consider this: the power of the universe lies within the smallest of particles. Charges push and pull on each other, but how strong is that force? Enter Coulomb's law, the rulebook for electric charges. Like magnets, charges interact more strongly when close, and weakly when far apart. The force depends on two things: the amount of charge and the distance between them. More charge means a stronger push or pull, more distance means a weaker force. Double the distance, and the force drops to a quarter, an inverse square law just like gravity. This law explains why a shock from a doorknob is so sudden. As your hand nears, the force spikes, making electrons leap across. Coulomb's law makes these zaps predictable, not random. It's a simple, elegant rule that governs every electric interaction. Next time you feel a spark, remember, it's science in action. The universe runs on these invisible pushes and pulls. Science is cool! Imagine two electrical charges separated by a distance. They exert a force on each other, either attracting or repelling. But how do these charges know about each other from a distance? What is the mechanism that allows them to interact without any visible connection? It's a fundamental question that puzzled scientists for a long time. The answer lies in the concept of electric fields. These fields are invisible, yet they permeate all of space around any charged object. Every charge, no matter how small, creates an invisible field around itself, a sort of aura that extends outwards in all directions. This field is a region of influence, a zone where the charge's presence can be felt. This field is constantly shaping how other charges move nearby, guiding their paths and dictating their interactions. It's a dynamic and ever-present force. Think of it like the smell of a freshly baked pie spreading through a kitchen. The pie is the charge, emanating something, and the smell is the field, spreading its influence. The closer you are to the pie, the stronger the aroma. The stronger the field, farther away, the scent fades and it's weaker. Now, imagine you place a test charge in the field and it immediately feels a push or pull, depending on its position relative to the source charge and its own charge. The field itself isn't matter. It's not something you can touch or see directly. Instead, it's a set of instructions filling space, a blueprint for how charges should interact. It's constantly telling charges how to behave, guiding their movements and influencing their interactions. This seemingly simple idea revolutionized physics. Because charges don't act directly at a distance, they create fields that then act on other charges. The field is the messenger, carrying the force and mediating the interaction. Whether it's the sun's gravity holding planets in orbit, or a charged balloon sticking to a wall with static electricity, fields shape the universe at every scale. This invisible architecture of forces is everywhere, constantly at work. Every interaction, from the smallest atoms to the largest lightning strikes, starts with a field. Understanding fields lets us map the unseen world, revealing the hidden forces that govern our reality. So let's delve deeper and see how we visualize these fascinating fields. To visualize electric fields, scientists use field lines, like drawing currents in a river. For a single point charge, field lines radiate straight out, positive, or in, negative, showing the direction a test charge would move. The closer the lines, the stronger the field. For a line of charge, like a charged wire, field lines shoot out perpendicular, forming a cylindrical pattern. The field from a point charge weakens with the square of distance. From a line charge, it weakens more slowly. These patterns help us map complex fields by combining simple shapes. Field lines give us an intuitive map of invisible forces. By understanding points and lines, we can tackle more complex arrangements. This is the foundation for exploring real-world electric fields. Let's measure how much field flows through space. So, how do we quantify the amount of electric stuff flowing through a given area? How do we put a number on this invisible force? Enter electric flux, a concept that allows us to do just that, to measure how much electric field passes through a defined area. It's a way of counting the field lines, giving us a tangible value to work with. Imagine catching rain in a bucket. This analogy helps to visualize electric flux. The intensity of the rain, or how much rain is falling per unit time, corresponds to the field strength. More rain, field strength. The size of the bucket, or its opening, represents the area. Bigger bucket, area, and the angle at which you hold the bucket relative to the rain also matters significantly. Hold the bucket straight up, directly in the path of the rain, for maximum rain capture. Tilt it even slightly, and you catch considerably less rain. It's the same principle with electric flux. Flux essentially counts the number of electric field lines that are passing through a given surface. So, if the electric field is particularly strong, meaning there are many field lines packed together, or if the area we're considering is large, then the electric flux increases proportionally. And just like with the rain, the angle at which the field lines intersect the surface matters a great deal. A surface perpendicular to the field lines catches the most flux, while a surface parallel to the field lines catches absolutely none. Furthermore, the materials present in the space can weaken the electric field itself, affecting the flux. To account for this, scientists often use electric flux density, often denoted as D, which allows us to focus specifically on the source charges that are creating the field, irrespective of the intervening materials. Thinking back to our rain analogy, D is like counting the raindrops as they leave the cloud, rather than just focusing on the ones that eventually make it to the ground. It's a fundamental and powerful way to measure the flow of an electric field, regardless of the properties of the medium through which it's passing. This concept of electric flux and flux density is absolutely key because it sets the stage for our next big shortcut, Gauss's law. So, let's dive in and see just how Gauss's law simplifies everything we've learned so far. Calculating electric fields for complex shapes is tough unless you use Gauss's law. Gauss's law links the total electric flux through a closed surface to the net charge inside. Imagine a sprinkler inside a sphere. The total water hitting the sphere depends only on the sprinkler, not the sphere's size. Any closed surface works, choose one that matches the symmetry of your charge. For a charged wire, use a cylinder. For a flat sheet, use a box or cylinder. The math becomes simple, thanks to symmetry. Gauss's law is a superpower for solving electric field problems. It turns complex calculations into easy ones. This shortcut reveals the deep connection between charge and field. Let's explore the energy behind these forces. Beyond force and field, there's energy, electric potential or voltage. Think of lifting a ball onto a shelf. You store energy by working against gravity. With charges, moving one against an electric field stores electric potential energy. The closer you push a positive charge to another positive, the more energy you store. Let go and the charge rolls downhill, converting potential to kinetic energy. Voltage measures how much energy a charge has at a point. High voltage is like the top of a hill. Charges naturally move from high to low potential. A battery creates this difference, pushing charges through circuits. Connect a wire and charges flow, releasing energy as light or heat. Voltage is the push that drives current. Every spark, every light bulb runs on this stored energy. Let's map out these electric hills. To visualize voltage, we use equipotential surfaces, places where every point has the same potential. It's like walking along a flat path on a mountain, no energy needed to move sideways. For a point charge, equipotentials are concentric spheres, like onion layers. Electric field lines always cross equipotentials at right angles, pointing downhill. The closer the equipotentials, the steeper the hill, the stronger the field. Where they're far apart, the field is weak. The potential gradient tells us how quickly voltage changes. Steep means strong field. Mapping voltage lets us see the strength and direction of electric fields. Equipotentials and field lines are two sides of the same coin. This helps us understand how energy moves in electric systems. By reading these maps, we can predict how charges will behave. Let's wrap up our journey. We've journeyed from simple charges, our universe's Lego bricks, to the rules that govern their push and pull. Coulomb's law gave us the math, Fields gave us the map, and Gauss's law gave us shortcuts. We saw how voltage stores energy and how equipotentials reveal the electric landscape. These aren't just textbook ideas. They power our technology and explain the chemistry of life. From lightning to smartphones, it's all about charge, field, flux, and potential. Simple analogies, Legos, sprinklers, pies, and mountains help us grasp these deep truths. The invisible architecture of the universe is built on these principles, and that's what makes electrostatics so incredibly cool. Consider it.